Denoising diffusion probabilistic models have revolutionized image generation, producing visuals so lifelike they blur the line between real and synthetic. But here's the catch. High visual fidelity doesn't mean semantic accuracy. In this video, we dive deep into a critical blind spot in AI image generation: identity preservation. Specifically, we explore how even state-of-the-art diffusion models can generate photorealistic faces that look almost right, but are completely wrong in identity. Our focus: K-pop idol face generation, a domain defined not by broad categories like man or woman, but by razor-thin distinctions between individuals who share near-identical features, similar skin tones, makeup styles, lighting, and hairstyles. This isn't just about generating faces, it's about generating specific faces. And yet, standard evaluation metrics like FID and inception score fail spectacularly here. Why? Because they measure distributional similarity, not identity correctness. A model could generate 10,000 flawless images of someone who looks like Jungkook, but if they're all actually Jungkook's cousin, the metrics won't catch it. So we ask, how do we actually measure whether a model generates the right person? Our answer is relative classification accuracy, RCA, a calibrated metric that turns a trained classifier into a semantic oracle. Here's how it works. We first train a high-performing ResNet classifier on real K-pop faces, say 32 times 32 images from the Co-in-10 dataset, which contains 10 identities. This classifier becomes our ground truth judge. It learns to distinguish between, say, Karina and Heechul, not because it knows their names, but because it has learned the subtle, high-frequency features that define them. Now, we generate 5,000 images per identity, using a class-conditional DDPM. Then, we feed those synthetic images into the same classifier. If the model truly preserves identity, the classifier should recognize them as belonging to their intended class. But here's where things get revealing. The classifier achieves 76.8% accuracy on real data, a solid baseline. But on generated images, only 20.77%. That gives us an RCA of 0.27, meaning the model retains only 27% of the semantic identity information present in real data. That's not just low, it's alarming. And the breakdown shows even deeper problems. For some identities like Class 1, the model performs relatively well, achieving an RCA of 0.55. But for others, Class 2, for example, RCA drops to 0.02, with only 1.5% of generated images correctly classified. Why? Let's unpack the failure modes. First, resolution constraints. At 32 times 32 pixels, fine details, eye shape, skin texture, subtle jaw contours, are compressed beyond recognition. The model sees a blurry, averaged face, and generates a mean face that captures global structure but loses identity-specific signals. Even the Oracle classifier struggles with certain classes at this resolution, suggesting that identity itself becomes ambiguous when resolution is too low. Second, intra-gender ambiguity. Misclassifications cluster within gender groups. A model might generate a long-haired woman with a soft face, but confuse her with another long-haired woman, not because the model is broken, but because it's learned demographic categories before identity. The latent space prioritizes young female with dark hair over specific person. This hierarchical learning is powerful, but dangerous in fine-grained tasks. Third, class bias and mode dominance. The model shows a strong preference for certain identities, classes 0 and 1, generating far more samples that get classified as those identities, even when conditioned on other labels. This is partial mode collapse. The model isn't just failing, it's gravitating toward the most stable, visually consistent manifolds, like a magnet pulling toward the strongest signal. And this isn't just theoretical. When we visualize the confusion matrix of generated samples, we see a clear directional collapse. Misclassifications aren't random. They follow patterns. Class 2 looks like Class 1, Class 3 like Class 6. These aren't errors in the model, they're reflections of inherent dataset ambiguity. At 32 times 32, some identities are simply hard to distinguish. So what's the way forward? We propose two key directions. First, integrate metric learning objectives like ArcFace loss. Instead of just predicting pixels, we train the model to push identity embeddings further apart in feature space, enforcing larger angular margins between classes. This forces the model to learn discriminative features beyond general appearance. Second, adopt a cascaded diffusion architecture with super-resolution stages. Generate at low resolution first, then upscale through multiple refinement steps. High-frequency details like eyelashes, pores, and precise facial geometry are recovered during upscaling, giving the model the resolution it needs to capture identity. This isn't just about better visuals. It's about semantic accountability, ensuring that conditional generation doesn't just look real, but means what it's supposed to. Our work shows that visual quality metrics alone are insufficient. In fine-grained domains, you need a calibrated semantic metric like RCA to detect when a model is generating the wrong person, even if the image is photorealistic. This isn't just about K-pop idols. It applies to virtual avatars, digital twins, synthetic data for facial recognition, and any system where identity matters. The future of generative AI isn't just about realism, it's about truthfulness. And that starts with measuring what truly matters, not just how it looks, but who it is.